I guess we'll get started. So we have a test here on Friday, covering chapters 7 through 9 and 11 through 13. And today we're going to move on to chapter 14, which is when we start dealing with probabilities. Okay. No, this chapter 14 will not be on the test on Friday. Okay. I guess before I get into the material, are there any questions on anything? Yeah.
A simple random sample and representative. The data got from simple random sample is representative? Or?
Simple random sample. So simple random sampling does not guarantee a representative sample. The goal is always to get a representative sample, but a simple random sample does not guarantee that. However, we would expect a simple random sample to be representative. So just
if we
like
want to do a survey on campus, so we have different races, we have a certain ratio of male and female.
okay.
What kind of those from those four methods we want to recommend do a survey on campus?
I guess it depends.
If you want the data fully representative.
So simple random sample is probably sufficient for most cases. If you feel like the survey that you are the questions that you are asking in your survey are racially, quote, sensitive in terms that the demographics will make a difference in your answers, then you might choose to make a stratified sample. Or if you think the questions in your survey will be affected by the gender of the person, then you'd want to do a stratified sample just to ensure that you have a certain proportion of males and females. But if you have no reason to suspect that, there's no real reason to force or to do a stratified sample. That just kind of complicates things, and so simple random samples should be sufficient for most.
Representative. Have some representative.
Yeah, just like if I flip a coin 100 times, I will not necessarily get 50 heads and 50 tails. But I'm expecting something close to that. Is it possible that I end up getting 70 heads and 30 tails? It's possible, but it's unlikely. Okay. So when we take a simple random sample, is it possible to get a sample that's not representative? It's possible, but for it to be highly different is unlikely. Okay. We're expecting something to be similar to the population. Okay, so probability. There's a bunch of rules in terms of calculating probabilities of different events, and then we also have empirical probabilities and theoretic probabilities. So let me just make a small distinction between theoretic probabilities So theoretic probabilities are probabilities that we calculate using quote rules or axioms of probability. So, for example, with a coin flip, the probability that the coin lands heads is equal to 0.5. This is a theoretic probability. Okay. On the other hand, we have empirical probabilities. And these are probabilities based on evidence. Generally, the relative frequency of an event after many trials. Okay, so for example, we could actually flip a coin say 10,000 times. It lands heads. Uh, 5,043 times. So the empirical probability is equal to 5043 over 10,000, or 5043. Okay, so we have the theoretic probability and the empirical probability. When we're talking about a theoretic probability, and I say that the probability of an event, such as the coin landing heads, is equal to 0.5, what exactly are we referring to? Yeah, so in our class we take on what we call the frequentist view. Of probability. And so whenever we say something like there's a 0.5 chance or 0.5 probability that the coin lands heads. So if I say the probability that the coin lands heads is equal to 0.5, that refers to the long run relative frequency. Meaning, if I were to flip the coin an infinite number of times and calculate the relative frequency of how often it lands heads, the relative frequency will be 0.5 after an infinite number of trials. Okay, so but of course, we cannot do anything an infinite number of times in our real world, in our lifetime. But this is the idea of a frequentist view, is that if we do this many, many, many times, we are looking at the overall relative frequency to be 0.5. So a lot of our notions of probability come from the idea of many repeated trials. Okay. There is a notion called the law of large numbers, which ties the theoretic probabilities to empirical probabilities. Okay. So we have the law of large numbers, which states that the empirical probability of many, many samples will approach the theoretic probability. Okay, it sounds reasonable and maybe very simple, but that's just the general notion of the law of large numbers. So the empirical probability or in other words, the relative frequency of an event based on trials that you have done, the empirical probability of an event will approach the theoretic probability as we increase the number of trials. Maybe instead of, instead of say will, say is expected to approach. Just because, for example, after 100 coin flips, it is possible that we have observed 50 heads and 50 tails. Okay, so in that case, the empirical probability of heads is 0.5, and that's as close as we will ever get to the theoretic probability is equal to it. Okay, and after 1,000 coin flips, maybe we've seen 503 heads and 497 tails. So therefore, my empirical probability of heads is a little different. So it's not any closer. But overall, we would expect that after 1,000 coin flips, the empirical probability to be closer to the theoretic probability than after only 100 coin flips. Okay, so after 100 coin flips, we're expecting a little bit more variation in the empirical probabilities, but as we increase the number of trials, we expect the empirical probabilities to be even closer to the theoretic probabilities. Is that okay? All right. The law of large numbers is not to be mistaken with what we call a gambler's fallacy, which would be that if I flip a coin, let's say I flip a coin 20 times, and I see a whole bunch of heads. Maybe I see 15 heads. Okay, so this is an unusual happenstance. But after 20 coin flips, it's possible that the coin landed heads 15 times. Okay, gambler's fallacy would say, go something along the lines of, it must even out, therefore we would expect to see tails more often. Okay, that is an incorrect notion. Okay, the law of large numbers states that we're expecting the empirical probability to approach the theoretic probability. And the way this works is that if you see something unusual, for example, in the beginning you see too many heads, how can we reconcile that with, after more coin flips, it's going to be closer to the actual probability without explicitly stating that tails is now more likely. Okay, it's just that after many more coin flips, the future coin flips we're all expecting to be 0.5 heads and 0.5 tails. And if you do a whole bunch more, whatever you get over there is just going to overwhelm anything unusual that you saw in the beginning. Okay, so it's not that the forces of the universe are trying to even out things. It's just that in the future we're expecting the same probability of 0.5 to exist, and whatever happens in the future we're expecting to overwhelm anything unusual that you see in the beginning. Okay, so yeah, so but a lot of times, so if you go to Vegas, it's fun going to Vegas anyway. You play, like, if you go to a roulette table, every roulette table has like this electronic display of the past numbers that have come up. Okay, and that's all there to play mind games with you. Okay, because if the ball has not been tampered with and the table operates as it should, every single one of those spots has an equal probability of being selected. Okay, and what has happened in the past has no bearing on what happens in the future. And the casinos know this, and that's why they run the games. But us being foolish humans, hoping that we can, I don't know, game the system, we look at the past numbers, and maybe that influences what we select in the future. Okay, but the truth is it doesn't matter. You could just close your eyes and pick numbers, and you'll be equally likely to be correct as somebody who, I don't know, asks the stars what numbers they should select. So, law of large numbers, that's how the casinos stay in business, because even if somebody gets lucky, quote-unquote lucky, in the short run, in the long run, they know that the theoretic probabilities will hold. Okay. Alright, so calculating theoretic probabilities. We'll start off with the most simple examples. Okay, so we have random events or random experiments with simple outcomes. So simple outcomes means every outcome that's possible is equally likely. So, flipping a coin, your outcomes are heads versus tails, and they are equally likely. Rolling a die, you can get 1 through 6. They're all equally likely. Or selecting a random card. From a standard deck. Each of the 52 cards is equally likely to be selected. Okay, and so if we group some of these together into a single event, so we could define some event A as maybe we've selected a face card. So a face card is the Jack, Queen, and King. Aces are not face cards. There's no face on the ace. It's a high value card. So face card, Jack, Queen, King in each of the 4 suits. And so the probability of selecting a face card is equal to 12 out of 52. Okay? There are 12 face cards. 12 out of the 52 cards in the deck are face cards. Each card is equally likely to be selected. So the probability of selecting a face card is 12 out of 52. You could reduce that to 3 out of 13. It doesn't matter. Or turn it into a decimal. They are all saying the same thing. For simple outcomes, the probability of some event A, is equal to the number of simple outcomes in A divided by total number of outcomes. So this is I think you guys probably already knew these rules regarding simple outcomes of probability, but things aren't always simple outcomes, and so we have even more rules and things like that. Okay, just a few rules. If we've got some event A, we call that A. We also have the complement of A. Okay, complement is spelled with an E here. It is not something nice you say, but it comes from the idea of completing. Okay, so there's A and the complement of A. They complete each other, quote, quote, quote. So the complement of A is the event that A does not happen. Okay, so we often write this as not A, or A complement, or A prime. Okay, these are just different notations for the same thing. The book uses A complement. I think not A is easier to understand, but whatever event it is, there's only two possibilities. Either it happens or it doesn't happen. Okay? And so the two probabilities, the probability of A plus the probability of not A, that accounts for everything that's possible, so the total probability between those two things is 1. Okay? And that gives way to the probability of any complement. The probability of not A is equal to 1 minus the probability of A. Okay? So if we take into account everything that's possible, it must be 1. Okay? Because something is bound to happen. I guess I will state this now. So all probabilities are between 0 and 1 inclusive. If it's 1, it means it always happens. If it's 0, it never happens or is impossible. And everything else is in between. Okay? So if in your calculations you ever get a probability that's less than 0 or a probability that's greater than 1, you have made a mistake. Okay. We have quote-unquote OR rules. So we could ask a question, what is the probability of A or B happening? So we would write this as the probability of A or B. Okay. This can be, oftentimes we draw Venn diagrams to illustrate this. So this box represents everything that's possible. So the total area in the box is 1, or we call this S to describe the space of the universe or whatever. And we have A and B. Okay? So the probability of A or B would then be equal to whatever's in this joint area. Okay. So the probability of A or B, we can say it's equal to this plus this plus this. Okay, so that's one way. Or we could say it's equal to, this would be A plus B plus or minus, because I've double counted this, I have to subtract off the overlap. So this is A and B. So we often write this is equal to the probability of A plus the probability of B minus the probability of A and B. Sometimes you will see this written as A union B. And this might be written as A intersection B. The cuff and the cap, I don't know if you guys are familiar. It doesn't matter. Okay. We won't worry too much about this. This is A and not B. This is A and B. This is B and not A. If we're breaking it out into that way. And then we have special case of the OR rule. A and B are disjoint, also called mutually exclusive. Okay. Disjoint or mutually exclusive means that the probability of A and B is equal to 0. Or if we were to draw a picture, here's A and here's B. There's no overlap between A and B. So A and B are mutually exclusive. So there's no overlap. So that reduces our A or B equation to just probability of A plus the probability of B. It's exactly the same over there, except now we are minusing 0, so we can leave that out. Okay, so let's try something out. Let's say we pick a random student. And let's say the probability that the student lives on campus. I don't know, what do you think, what percentage of students do you think live on campus? 20? I have no idea.
41.
40? 40%? Okay. That's a lot. Alright, and then what else? Probability that we'll say a STEM major. I don't know. Let's say 35. And probability of on-campus and I can spell. Let's say is 18. Okay. So what is the probability that a student lives on campus or is a STEM major. And I'll say, what is the probability that a STEM major, that a student is a STEM major, but does not live on campus? Okay, so what's our answer over here? 0.40 plus 0.35 minus 0.18, so I get 0.57. Is that what we got? So lives on campus plus STEM major minus any overlap. I get 0.57. Okay. And what's the probability that a student is a STEM major but does not live on campus? So this would be 0.35 minus 0.18, 0.17, right? So if we were to draw, I guess, pictures here, this would be this plus, this is what we're going for. So we do this plus this minus this. Over here, what we want, so this is on campus, and this would be STEM. We want, is a STEM major but does not live on campus, so we only want this part. So this is going to be equal to this minus this piece. Minus the overlap. Okay. On the other hand, we have AND rules for probability. Okay, so we have the OR probability rules. We have the AND probability rules. Just want to make sure. Two independent events. Oh, they don't cover conditional probabilities in this chapter? Okay. Even more stuff. Alright, so we have AND rules. So we might ask, what is the probability of A and B? Okay. And so first we're going to learn the special case for when A and B are independent only. Okay? So when A and B are independent. So independent means that the outcome of A has no influence on the outcome of B, and vice versa. The outcome of B has no influence on the outcome of A. So the probability of A and B, if they are independent, is equal to the probability of A times the probability of B. So an example could be, I flip a coin twice. What is the probability I get heads on the first flip and heads on the second flip? So this would be probability of heads on first and heads on the second. So this would equal, because the outcome of the first coin flip is independent of the second coin flip, we can apply this multiplication rule, or this rule for the AND rule for probability. So this would be the probability of heads on first times the probability of heads on the second flip. And so I do 0.5 times 0.5, and I get 0.25. I guess we'll do the conditional probabilities next week. Okay, so let's just try an example here, and we'll wrap up. Okay, so you can buy some what is it? Starburst candies, and they have what? They have the all reds, right? Because the reds are the best. So, okay. Well, you have cherry, strawberry, and is there another flavor? Orange. Okay.
Yellow.
Huh?
Yellow.
Yellow. Oh, yellow's the worst. All right. Okay. So let's say the probability. We're just going to call this probability of cherry is 35%. Probability of getting strawberry will be 40%, and the probability of orange 25%. That adds up, right? Yeah. Okay. Okay, so let's say we have a huge bag. Okay. Huge bag with these probabilities of candy. Okay. And I say huge bag because technically, once you draw the first candy out, you've taken a cherry candy out or something, what's remaining is technically no longer the same as the original bag, okay? But we're going to just say it's so huge that whatever change it brings in is negligible, okay? So that we can assume that the probability of drawing a cherry candy is 0.35 every time we reach into the bag because it's so huge. Is that okay? All right. Huge, so the probabilities will not change. Okay, so let's say we draw 3 pieces of candy. What is the probability that the first candy is not cherry? Okay. What is the probability that the third piece of candy is the first orange piece I get? I guess I'll answer these as we go along. Okay, what's the probability that the first candy is not cherry? This one should be easy. 0.65, right? So we do 1 minus the probability that it is cherry, and we do 1 minus 0.35, and we get 0.65. That's easy enough. Okay, what's the probability that the third piece of candy is the first orange piece that I get? So in order for this to happen, what has to happen? The first two pieces of candy have to be not orange, right? So the sequence has to be not orange, and then orange. That's the exact sequence that must happen. So what is the probability that the first candy is not orange? 0.75. Okay. And what's the probability that the second candy is not orange? Also 0.75. And the probability that the third candy is orange is 0.25. So this is the sequence that must happen. 0.75, 0.75, 0.25. Okay? Let's see, what else could I ask? Alright, so what is the probability that all three are cherry? What would we do there? 0.35 times 0.35 times 0.35, right? If we're drawing three pieces of candy. Okay. What is the probability that none of the three are cherry? How would I solve that one? So I would do 0.65 times 0.65 times 0.65. So keep those in mind. Alright, I'm going to complicate this. We're still drawing three pieces of candy, still the same probabilities. Okay, what is the probability that after drawing three pieces of candy, what is the probability that I have at least one cherry candy? Oh, sorry, at least one.
1 minus 6.
Yeah. Okay. So getting at least one cherry candy is the complement of getting no cherry candies. Alright? So when we drop three pieces of candy, at the end of the day, only one of two things can happen. I either get no cherry candies, or I get at least one. Okay? Because at least one includes 1, 2, or 3 cherry candies. So either I get no cherry candies, or I get at least one. So at least one is the complement of none. So probability of at least one cherry is equal to 1 minus the probability of, I know this is not correct to write, but none cherry. So this would be 1 minus 0.65 to the third. Okay, I think that's it for today's lesson on probability. We'll cover more probability steps on Monday, and until then, study for your test, quiz, or whatever we have coming up on Friday.
Thank you.
See you guys.